There's also delta G under standard conditions, which you calculate the same way you did delta H and delta S under standard conditions, the sum of the products minus the sum of the reactants. If your temperature is other than 25 degrees, sometimes it's easier just to take the delta H under standard conditions minus your new temperature times the delta S under standard conditions. And we can also add reactions together to get the delta G. Delta G is a state function. So let's work through some problems. We have a reaction, sulfur dioxide plus 1/2 oxygen goes to sulfur trioxide. We have a delta H of negative 98.9 kilojoules, delta S naught of negative 94 joules per Kelvin at 25 degrees Celsius. Calculate delta G at 125 degrees Celsius and determine if it is more or less spontaneous than at 25 degrees Celsius when delta G is negative 70.9 kilojoules per mole of sulfur trioxide. So we're going to be using our delta G under standard conditions is delta H naught minus T delta S naught. So our delta G is going to be negative 98.9 kilojoules minus our temperature, 125 degrees Celsius, is going to be 398 Kelvin times our delta S is negative, if I switch it to kilojoules, 0.094 kilojoules per Kelvin. 940 technically. There we go. So my delta G under standard conditions at that temperature works out to negative 61.5 kilojoules. And so we are still spontaneous because we're still negative, but less so than we were at the lower temperature. All right, another practice one here. Determine the free energy change. So that's going to be my delta G in the following reaction at 298 Kelvin. So 2 water plus oxygen goes to 2 hydrogen peroxide. So I'm going to want to find my delta H under standard conditions is going to be 2 times my peroxide, negative 136.3, minus 2 times my water, negative 241.8, and then my oxygen is 0, so I don't have to worry about that. So my delta H is a positive 211 kilojoules per mole. Not per mole, just kilojoules. The per mole gets taken out with my coefficients. My delta S is going to be 2 times my peroxide, 232.7, minus 2 times my water, 188.8, plus my oxygen, 205.2. So my standard delta S is negative 117.4 joules per mole. So my delta G is going to be, I'm going to change over to joules this time. So 211,000 joules minus my temperature, 298, times negative 117.4, which works out to 2.46 times 10 to the 5th joules, or 246 kilojoules. So we also have standard free energies of formation, our delta G of formation naught, which is the change in free energy when 1 mole of a compound forms from its elements in their standard states. Just like with delta H, for delta G, the free energy of formation of pure elements in their standard states is 0. So we can do with delta G like we've done with delta S and delta H, use a table. So I would recommend pausing the video, practicing this again. So our delta G of formation, or delta G for this reaction from the delta G's of formation, is going to be carbon dioxide, negative 394.4 plus 2 times water, that's parenthesis, negative 2 water in the gas phase, 28.6, plus 4 times ozone, plus 163.2, minus my reactants, which is methane, negative 50.5, plus 8 times 0 is 0. So my standard delta G is going to be, I'm going to add up all my products a second, is equal to negative 198.8 plus 50.5, which works out to negative 148.3 kilojoules. Right? Back to our formation of hydrogen peroxide, determine the free energy change at 298 Kelvin, and now we're given the standard enthalpy of formation. Or sorry, not standard enthalpy, standard Gibbs free energy of formation. So we'll take 2 times our product. Oh, sorry, that's our reactant. 2 times our product of peroxide minus 2 times our reactant that has a number. So our delta G standard is 246 kilojoules, which is the same thing we got doing it the other way. All right, what about relationships with delta G? The relationships with delta G are the same as the ones you learned back in Chem 103 for delta H. If a reaction can be expressed as a series of reactions, the sum of the delta G values of the individual reactions is the delta G of the total reaction. In other words, delta G is a state function. If you reverse a reaction, you change the sign on delta G. If you multiply your reaction by a factor, you multiply delta G by that same factor. So same rules as for delta H. So determine the free energy change in the following reaction at 298. Again, it's our reaction of water and oxygen to form hydrogen peroxide. For this one, we are going to want to, for this reaction, we want 2 peroxides. So we're going to multiply all of this by 2. And then for my bottom one, I want water as a reactant, so I'm going to reverse it. So 2H2O goes to 2H2 plus O2, and that's going to make my delta G positive for 57.2. If I add my 2 reactions together, I'm going to cancel things out here. So I have 2 hydrogens on that side, 2 hydrogens on that side. Then if I add everything together, I have oxygen plus 2 water goes to 2H2O2, which is the reaction I am looking for. And so my delta G, 105.6 times 2, negative 105.6 times 2 plus 457.2 gets me 246, which is the same, 0.0, which is the same number I got doing it the other ways. So, same answer. Now, why do we call it free energy? It's the maximum amount of energy released that's available to do work. For exothermic reactions, some of that heat release due to enthalpy is going to go into increasing the entropy of the surroundings, and so it's not available to do work. And generally, so free energy is the maximum amount. Often we can't even realize the full free energy available to do work. So here's an example. If we combine graphite and hydrogen to make methane, the delta H is negative 74.6 kilojoules. It's exothermic, but it's unfavorable because you're going from a gas, 2 molecules of gas to 1. But it is spontaneous, so the maximum amount of work that can be taken out of this process is 50.5 kilojoules. You're going to lose at minimum 24.1 kilojoules to the surroundings in order to make the reaction happen.